Hi, welcome back to another Study with Me session. My name is Amy. I'm the head maths tutor at Pinnacle Coaching College. So what I've got for you today is another revision session on the topic trigonometry, and specifically we're going to look at solving trigonometric equations. So the focus of this session is about looking at the very typical exam questions in this area, both at the advanced maths 2 unit level as well as the extension 1 level. So if you do advanced maths, I think you can stop at the point where I'll indicate when the questions become extension, or if you're interested in challenging yourself, more than welcome to have a look at the extension version as well. All right, let's get straight into it. All right, so before we look at how to solve equations, I think trigonometry is one of those areas which I find a lot of students do struggle with, especially when they learn it for the first time. But it's such an important topic because I've also seen a lot of students where they haven't sort of fully understood how to solve trig equations, and that carried on into year 12. And when the more advanced content comes, which involves doing derivatives or calculus on trig functions, that's when you sort of see those students who's got a solid foundation as to what trigonometry is about, and those who kind of didn't really fully understand. So I do think going back to the basics is fairly important in this particular topic. So before we dive into questions, I know this is meant to be revision, and I'm hoping you already know these basics, but just bear with me while I go through some of the basic concepts in case you don't fully understand some of the inner workings around how to solve trig equations. All right, so there are two concepts, right? So the first concept is what I would call the ASTC rule. So the ASTC rule, so a lot of you would have seen sort of the acronym All Stations to Central, but what they basically are is they tell you which ratio is actually positive in which quadrant. So now we work in this direction if we're looking at positive angles, so 0, 90, 180, 270, 360. Okay, so we operate in that anti-clockwise direction. Now I won't go into too much depth about that because that's not the focus of today. If you have negative values, you actually go in the clockwise direction. So it would have been minus 90, minus 180, minus 270, and minus 360. All right, but that's not the focus. We are just going to focus on the positive angles today. All right, so what does ASTC actually stand for? So A means all ratios are positive. So you can actually use a calculator to test this, right? So any angle between 0 and 90, if you chuck it into the calculator, you go sine 30, for example, cos 30, tan 30, they're all going to be positive answer. All right, so positive for all ratios. Okay. The S quadrant, second quadrant, that's what it's called, is sine ratio is the only positive one, and tan and cosine are actually negative. So think of an angle between 90 and 180. Let's say 120. Yeah? Check it in your calculator. Type in sine 120, and then cos 120, and then tan 120. You'll find that sine is the only one that is positive, whereas the other ones, cosine, tan, are actually negative. All right. So for example, cos 120 is actually negative a half. So that's what I meant. All right. So by the same sort of logic, right, you kind of get the point here. T quadrant, third quadrant, tan is the only positive ratio here. And the others, sine, cosine, negative. Okay. And then finally, the fourth quadrant, cosine, C, is the only positive ratio. So think somewhere between 270 to 360, 330 degrees, for example, right? You type in cos 330, it should be a positive number, whereas sine and tan are actually negative numbers. All right, so that's the first consideration when it comes to solving any trig equations, right? Which quadrant you're in, yeah, just noticing the anti-clockwise rotation, and once you work out which quadrant, what is the sign of your particular function, okay? Now, the second concept is the concept of a reference angle or related angle. So, let me give you an example. Let's think about the angle 120 degrees, okay? So we start counting from here. All right, so 120 degrees is from 0 into the second quadrant, so that's 120 degrees. So what is termed the reference angle is that acute angle it makes with the horizontal axis. All right, so if you go 180 minus 120, oops, sorry. Your reference angle is 60. So your reference angle is always going to be an acute angle. And that's actually going to indicate the value of your answer when we do the calculations later. And the concept of a reference angle is really important. Now, the key feature of a reference angle, let me just sort of generalize this for you. Yeah. So let's think about all four quadrants. Okay. And I'm going to sort of take the same example, right? Let's think about 60 degrees, 120 degrees, 240 degrees, 300 degrees. Now, they all have the same reference angle, 60 degrees. So the reference angle in the first quadrant is that angle there. The reference angle in the second quadrant is this one. That's the third one. And that's the fourth one. All right, so those are the reference angle in the four respective quadrants. Now, why is this actually important is, let me give you an example. If you think about what cosine 60 is, cosine 60 is a half. Okay, you'll find that cosine 120 is negative a half. Cosine 240 is negative a half. And then finally, cosine 300 is a half. Okay, so notice when your reference angle is exactly the same, they all produce the same number, a half, right? And depending on the quadrant you're in, so let's think A, S, T, C. In the A quadrant, it's a positive a half because all ratios are positive. In the fourth quadrant, in the C quadrant, it's also positive a half because cosine is positive in the fourth quadrant. And then you've got the other two, which is only sine and tan are positive in those quadrants, so cosine are negative in those quadrants. Okay, so that's why the importance of a related, the concept of a related angle is important for that reason. All right, so hopefully that makes sense. So let's move on to some exam questions in this area so we can see how it's solved. Okay, so let's start with this one here. So I'm going to initially start solving some of these questions in degrees and then we'll sort of transition into radians, which is another measure for the angles. All right, so in any trig equation, your ultimate objective is sort of two things, right? You need to express it into a single type of ratio. So you have a combination of sine, cosine, and tan. You need to use identities to simplify first, yeah? And then you have to make it the subject, which is this case. So we've got a single ratio question here, just cos x. So you need to make it the subject, right? So let me just copy the question. All right, so I'm going to move the 1 across first. Divide the root 2 across. All right, so that's it. Now, a lot of people make the mistake of just throwing this into the calculator. I mean, the calculator will give you an answer, but not necessarily the answer in between the domain, not necessarily all the answers. So I'm going to help you sort of figure out how to use the calculator properly in conjunction with the previous knowledge. So two-step process, right? Step 1, Which quadrant are we in? All right, so cosine is negative, so you should be in the second and the third quadrant. Yeah, where cosine is negative. Second, you need to work out the related angle. All right, so how do you calculate the related angle? So you can actually just use the calculator for this. So I recommend putting in inverse cosine 1 on root 2, so shift cos 1 on root 2 without the negative. All right, because that will always give you a first quadrant answer, and that will be much better to work with, less confusion. So it should come out 45 degrees. All right, so then how do I interpret both two steps and turn that into answers? So I'll do on this side. So we should be in the second and the third quadrant with a reference angle of 45 degrees. All right, so don't forget this is at 180, right? So this is 90, this is 270. All right, so X would be, so second quadrant, you're quoting that answer there, right? Which is basically 180 minus 45 degrees. And then the third quadrant, you're quoting that angle there, which is 180 plus 45 degrees. All right, so that's it. So put that into the calculator. That's 135, or you can do it in your head. It's not that hard. Okay, 225. That is it. All right, so this is the most basic type. Single ratio, make it the subject. Look at the quadrant, look at the related angle, and then just work out the answers corresponding to the quadrants you're meant to be in. All right, so let's move on to something slightly more advanced, like this guy here. All right, so this guy here will require you to apply some of the basic identities. So generally speaking, try to convert everything into sine, cos, or tan, or even sometimes tan. It kind of depends on what it is. You might want to go back to the basic sine and cos. Sine, cos tend to work the best because they have the most identities. So for example, in this one, sec. What is sec? Sec is 1 on cosine. All right, so sec squared is 1 on cosine theta squared. Okay, so what I'm going to do is I'm going to flip both sides. And then I'm going to square root. Now, remember when you square root, it's plus minus. All right, so that's the same as plus minus 1 on root 2. Okay, so the fact that it's plus minus, what does that mean? It means we are in all 4 quadrants, right? Because it can be both positive and negative. We're in all 4 quadrants. Okay, so we need to work out all the answers in all quadrants. All right, so the reference angle. What is that? So it's actually the same as the question before. Inverse cos 1 on root 2, which should be 45 degrees. All right, so that's 45. That's 45. 45. 45. Whoops. Okay, and then you just work it out. All right, so I'm just going to manually show you first. So the first answer is 45. The second answer is 180 minus 45. Third answer, 180 plus 45. Fourth answer, I'll do it on the inside. You have to go right around the circle, get into the fourth quadrant, 360 minus 45. Okay, so let's write that out. All right, so that's basically it. That's all the answers in between 0 and 360. So I'm just going to simplify that. So you can see it's very similar to the answers from before, except we've got 2 extra answers because we're looking at 2 additional quadrants. All right, so 4 answers in total: 45, 135, 215, 315. All right, so let's look at another one. So this time, an adjustment to the domain is required. Now, how do I know that? So usually So if you compare to the question before it's a simple cos theta, right? Whereas this one is tan 2x. So if your function that's inside the trig function is not a straightforward single x or single theta, some sort of adjustment is required. So let's start by taking the original domain. So x is meant to be in between 0 and 180. And then what you do is, okay, it should be 2x, not x. So you times everything by 2 to adjust the domain first. Okay, so in other words, initially when you solve, it should be quoting answers between 0 and 360 degrees. All right, so keeping that in mind, we're going to try to simplify this first. So just like before, right, you need to make the ratio itself the subject. So divide the 3 across. And then square root that. Square root means plus minus. Yeah, which is basically 1 on root 3. Okay, so now you go through the same steps. Quadrants, reference angle, quadrants first. So quadrants, all 4 because it's plus minus. And then angle. Use your calculator if you need to, or you, like me, you remember the exact values. That should be 30 degrees. All right, so that's 30. 30, 30, 30. Okay, so I'm going to start going straight into it because I've shown you 2 examples that's quite detailed already. All right, so 2x. So this thing is equal to first quadrant, 30. Second quadrant, 180 minus 30. Third quadrant, 180 plus 30. Fourth quadrant, all the way here, 360 minus 30. Okay, so simplifying a little bit first. Now this is the value for 2x, but we're not solving for 2x, we're solving for x. So the last thing is divide everything by 2. So imagine divide the 2 across on every single answer. All right, that becomes 15. 75. All right, so 15, 75, 105, 165, and that's pretty much it. All right, so I hope that all makes sense. So let's have a look at another one. All right, this time it's a quadratic in terms of sine x, and this time I've got the domain in radians. So this is the first question where I'm going to start solving the answers in radian form. Now, if you're not too familiar with radian, remember the conversion. 180 degrees is equals to pi radians. That's essentially conversion. So if you have 30 degrees, it will be 30 degrees times pi on 180, which is pi on 6. Okay, so that's the radian equivalent answer. So this is in between 0 to 360 degrees. So what I'm going to do is I'm just going to solve this in radians first, and then I'll just also comment on the answer as though it was in degrees, just to help those of us who are not too familiar with radians at this point. All right, so you see single ratio, you only see sine ratio, which is good. Okay, you don't need to do any simplification. But then they're in different powers. So this is actually a quadratic equation. Now, if you can't quite see that, let u equals to sine x. So make a substitution, right? And then we're going to factorize this. Now, you can use whatever methodology you've been taught at school to try to factorize this. So I generally like the cross method. All right, so I factorize it, so u is minus a half or 2. Okay, but we're not solving for u, we're solving for sine x. So u is sine x, so sine x is equals to minus a half, sine x is 2. Now you'll find that there are no answers for sine x equals to 2 because if you think about the sine graph, right? It's better. The sine graph is actually in between 1 and minus 1. So since sine x is actually in between minus 1 and 1, this thing's not going to have any solutions. And you can try that in your calculator. It'll say math error. Okay, so we won't bother with that. We'll only work with this one. Okay, so this one, again, quadrants, ASTC. So I'm starting to not get into too much detail. Yeah, you've seen a couple of examples already. Okay, so sine x is negative in the third and the fourth quadrant. I need my reference angles. What are they? So my reference angle is going to be inverse sine a half. Yeah, you can use the calculator, which is pi on 6 or 30 degrees. Okay, so I'll write both. Okay, so then x is equal to, now I'm just going to express the boundary angles in terms of radians so that you can wrap your head around it. So it will be 0. Pi on 2 is 90 degrees. Pi is 180 degrees. 3 pi on 2, 2 pi. All right, so the third quadrant answer will be pi plus pi on 6. Yeah, pi plus pi on 6. And then the fourth one is all the way in the fourth quadrant, so 2 pi minus pi on 6, which is equivalent to 7 pi on 6, 11 pi on 6. All right, so that's the answer in radians. Now, if you're like, oh my god, I can't do radians, a little bit of cheat tip, do it in degrees and just do this conversion. Yeah, convert all your answers to radians at the end. But in any case, just in case you don't know what they are, that should be 210 and 330 degrees. Okay, so if you want to try that yourself, see if you can get 210 and 330. Just make sure that's right. Yeah, it should be right. All right, so hopefully that makes sense. So let's have a look at a more advanced question. A more advanced question quite often is like this. It's like a two-step process where there's like an identity proof in the first part and then you try to use that to help you solve. So we'll start with the identity proof first. Okay, so we're going to prove this. So proof layout. Now, I really hate it when students write the entire thing, so cos theta, tan theta equals sine theta, and then manipulate both sides, because that's not really a proof. You're just writing as though it's equal already. Yeah, a proof means you have to prove they are actually equal. So the preference here is to go left-hand side is blah, 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 which is the same as right-hand side. Or you can go right-hand side is blah, 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 simplify, equals to left-hand side. I don't care either way, just don't write both sides together. That just really irritates me when that happens. All right, so let's start with this. So left-hand side is equals to cos theta, tan theta. Now, the major identity for tan theta that converts it into sine and cos is sine on cos. Now, if you don't remember these identities, I believe they are on the reference sheet, so go check it out yourself. Make sure you are familiar with what's on it. All right, so cos theta cancels. You're left with sine theta, so right-hand side. All right, that's it. All right, so we're going to use this to help us solve. So we're trying to solve x sine theta, cos theta, tan theta equals to cosec theta. Okay, so we've already converted this part, remember, from the previous one. Yeah, so that's 8 sine theta times sine theta. I'll just leave that alone for now. All right, so this is from part 1. Then cosec theta. What does it represent? It means 1 on sine theta, right? Okay, so let's multiply the sine theta across. So it becomes sine theta cubed divided 8. Okay, so I'm kind of running out of room here, so I try to squeeze it in here. Okay, so then that means sine theta is equals to the cube root of 1 on 8, which is 1 on 2. Okay, so we're trying to solve sine theta is a half. So let's think about this again. Which quadrant are we in? ASTC, we're in the first and the second quadrant because it's positive a half. You can work out your reference angle by putting into the calculator inverse sine a half, which is 30 degrees, pi on 6. So theta is equals to the first quadrant answer, pi on 6. Second quadrant answer, pi minus pi on 6. 5 pi on 6. All right, so that's the answer in radians. And if you want it in degrees, that's 30 degrees, and I think that's 150 degrees. All right, so that's pretty much or as hard as it's probably going to get at the 2-unit level. So from this section onwards, I'm going to start looking at extension questions. So extension question, let's have a look at the next one. The extension questions generally, let me put it this way. The solve itself is not exactly too different. Yeah, how you approach it is still kind of the same. It's just it draws on identities you do in extension. That's pretty much it. So like for example, this one, right? Sine 2 theta is sine theta. So my general rule of thumb is try to convert things into a single type of ratio where possible. In this case, you also have a problem where one's a double angle, one's a single angle. So you use the double angle rule. So the double angle rule is sine 2 theta is 2 sine theta cos theta. That's the double angle rule. I believe that's not on the reference sheet, so make sure you remember these guys because they come in super handy. All right, so that's what we're going to do. We're going to convert that into 2 sine theta cos theta is equals to sine theta. Now, the most common mistake in this type of question is to then divide both sides by sine theta. What happens is when you divide both sides by sine theta, you actually tend to lose answers. So always avoid dividing by a ratio. Instead, do this. So let me just get rid of that. We don't want to do that. We don't want to divide by sine theta. We want to move everything to one side instead. And then factorize. So that creates two equations. Sine theta is equal to 0 and 2 cos theta minus 1 is equals to 0, which means cos theta is equals to a half. All right, so always move everything to one side and factorize rather than divide. Otherwise, you'll lose answers. You'll lose the answers relating to sine theta is equal to 0. Now, in any case, I haven't mentioned this earlier, but once you find the answers, if you're not sure whether they're right, you can always sub it back into the original function and see if it works for the equation. If it does, then you've got it right. All right, so let's start with sine theta equals 0. We haven't discussed this yet. This is boundary angles. Boundary angles usually happen. So what I mean by boundary angles is like 0, 90, 180, 270, 360. Right, so the boundaries of those quadrants, yeah? So generally, if you solve sine theta or cos theta to 0, minus 1, 1, that triggers boundary answers for tan theta. If you solve it to 0, that also triggers boundary answers. So those are really specific instances. Now, your calculator is only going to give you one of the many quite often. So be familiar with the graphs. For sine theta, the graph looks like that. Yeah, 0, 180, or pi, 2 pi, 360. Okay, and literally you just observe and the answer where is a 0. You can see is here, here, and here. All right, So that's it. That's it. You just observe, remember the graph and observe the answers. Sorry, I just realized I started doing things in degrees, radians. All right, so with this one, cos theta is a half. So again, let's start with quadrant, ASTC. Positive for cosine is first and fourth quadrant. Reference angle, use your calculator to assist you. It should be 60 degrees, so that would be pi on 3. Okay, so the answer in the first quadrant is pi on 3. The second one is from here all the way down to the fourth quadrant, yeah, where this is pi on 3. So that's 2 pi minus pi on 3. So that's pi on 3, 6 minus 1, that's 5 pi on 3. Okay, so that's it. 5 answers in total. 0, pi, 2 pi, pi on 3, 5 pi on 3. 5 answers. All right, so to summarize, first, use an identity to simplify the expression so that you can have the same angles, yeah, in your trig ratios. And second step, move everything to one side and factorize, never divide. And then you can solve individually. All right, so let's look at another one. Now this one comes up all the time. If you've learned this, is definitely going to come up. It's in every single HSC I've seen, or most of it, right? So it's standard auxiliary angle conversion. It has a lot of applications. So let's get into it. So the first one, we need to do the auxiliary angle conversion. There are 2 steps in an auxiliary angle conversion. All right, so we are trying to convert that into a single ratio. So first, use the compound angle rule. Expand it out first. Now, if you're not familiar with the compound angle rule, it is in the reference sheet. Oops. Now, I'm just going to swap these terms as I expand this, and same with this one. I'm going to swap these terms as I expand this, just so that you can clearly see what I'm doing here. Okay, so you want to look at sin x, sin x. What's attached to it? A cos alpha and 3. So that means A cos alpha is equals to 3. Okay, equating the coefficients. So same thing on the other one. Cos x, A sin alpha is 4. And then you put that over that. Oops, I just realized I wrote that wrong. So the A cancels, so sine on cos is tan. Now I know this thing asks for radians, but I think in the interest of making sure you understand it, I'll do it in degrees because I find that degrees is a lot easier to understand for most people. So that's 53/8. Yeah, if you want to convert it into radians, just times pi on 180. All right, so that's the angle alpha. How about A? How do you calculate A? Very easy. A is equals to, so it's basically, if you call that A and B, A squared plus B squared. It has its origins from Pythagoras. So the challenge for you today is try to figure out how is this Pythagoras. All right, so that should be 5. All right, so that means, so I'll just kind of do the conclusion down here. So that means 3 sine x plus 4 cosine x is equals to A, which is 5 sine x plus alpha. So I've just done it in degrees for the sake of making sure it's easy to understand. All right, so that's the first part, right? So now, what does that do? That converts a sine and cosine ratio that's been added together into a single ratio, which is incredibly important when it comes to solving. So the second part. All right, so we're trying to solve 3 sine x plus 4 cosine x is equals to 5 for in between 0 to 2 pi. So what I'm going to do is do it in degrees first, and then I'll convert it to radians in the end. All right, so right now the problem is you don't have a single type of ratio. That's hard to solve, and that's why you need auxiliary angle conversion. From before, we've worked out that this is 5 sine x plus 53 degrees and 8 minutes. Now, this is an angle that's not x, so theoretically what you should be doing is adjusting the boundaries by adding 53 degrees. Okay, I'm just going to add 53, that's roughly right. All right, so that's what you should do, but I don't think it actually affects the answers in this case. All right. So divide the 5 across is 1. 1 is a boundary angle, so let's investigate the graph. All right, 1 is there at pi on 2, or 90 degrees basically. All right, so that's where 1 is. So x plus 53, 8 is equal to 90 degrees. X is 90 degrees minus 53, 8, which should be about 36 degrees and 52 minutes. Yeah, in degrees. Or if you take this answer and times pi on 180, so actually type in pi on 180, yeah, so we get the radian equivalent, 0.64 in 2 decimal places. All right, so that's the radian answer, 0.64. So just to summarize, right? So the first part is the auxiliary angle conversion part. So the conversion is basically taking the 3 sine x plus 4 cos x and convert it into something in the format of a sine x plus alpha. Expand it using compound angle rule, equate the coefficients, create tan alpha expression which gives you the angle, and A is a very easy calculation, and then that's pretty much the conversion. Then the second part is then using the conversion in the actual solving, and then you work out the answer in degrees or radians depending on the requirement of the question. All right, so that's pretty much it on auxiliary angles. All right, last one for today. This one is a 5 marker, so a little bit more intense in this one. There's 2 parts, right? First part is an identity proof. Second part is using the identity to solve. So let's start with the first part. Now this one is actually a fairly typical proof. So with enough practice, I find that most people are able to get this one. You just know which identities to apply. All right, so the question kind of leads you in, asks you to look at the compound angle rule. So let's copy that. Okay, so the objective, if you look at this, is all in terms of sine theta. So coming back, pause for a bit. The double angle rule for cosine 2 theta actually has 3 versions. That is very, very handy. I'll remember all 3 versions because you use the different versions depending on what you're trying to achieve. All right, so that's the 3 versions of the double angle rule for cosine. So given that we are trying to express everything in terms of sine, you want to use this version here because it's purely in terms of sine, okay? So wherever I've replaced it with an identity, I will use a different color. All right, so this one, I'm going to use the double angle rule identity. And then the second one, sine 2 theta only has 1 double angle rule, thankfully, so no extra formulas to remember there. Oh, I was meant to do that in a different color, sorry. Let's expand. Okay, so let's health check our expression so far. You can see that that's sine theta tick, that's sine theta tick, that's sine theta, but you've got cos theta square. But that's okay. Remember the Pythagorean identity, sine theta square plus cos theta square is 1. So that means cos theta square is 1 minus sine theta square. So let's use that. So I'm trying to really squeeze this in so I don't need to flick over to the next page. So expand this. Okay, so I'm going to put the final line here. All right, so now you just collect the like terms. So sine plus 2 sine is 3 sine theta. And minus 2 sine theta cubed minus another 2 sine theta cubed is minus 4 sine theta cubed. That's it. Piece of cake, right? All right, so let's see the solve. So it goes hence solve. Let me just copy the question first. So sine 3 theta is 2 sine theta, 0 theta 2 pi. Now, a bit of exam tip here. A lot of, especially year 11s, you're not as used to doing exams compared to your year 12 friends. So what I do find is people tend to forget that a lot of exam questions structured like the one we saw previously is structured in a two-part. First one is worth 2 marks, and that's why I left all the marks there, just to show you and indicate how much they're worth and how difficult they're meant to be, right? 2 mark and 3 marker. Even if you couldn't get the 2 marker, you know the conversion. Sine 3 theta is that. So get the 3 mark, right? Stick that in there and just see if you can solve it. That's what I would do. Don't completely wipe off 5 marks because you couldn't do the first part. All right, so that's a little tip from me. Always attempt the subparts. Yeah, because usually a lot of exam questions have the results written in the questions themselves. So just use it and move on. You don't have to prove everything. Yeah, move on and get those 3 marks, right? Imagine 3 out of 5 versus 0 out of 5. That's a huge difference. That's the difference between pass and fail. All right, so I'm going to stick in the identity. And I know my students love hearing what I say about fake it until you make it. And a lot of these like proof things, you're like, oh my God, I have no idea what I'm doing. I'm going to move everything to the right side. So I have no idea what I'm doing. Well, that's okay. How do you know I know what I'm doing, right? So it is about sometimes faking it until you make it. And sometimes as you're faking it, you eventually, oh, I didn't see this before. Now I see it. And you actually got out the real answer. So fudging it sometimes really works. So from here, all right, so like the comment I made before, never divide, always factorize. So we're going to factorize. And then we're going to solve the components to 0. So I'm going to do this on this side because that might need a bit more room to do. And to be honest, the new syllabus is a lot easier compared to what it was before. I was just having a discussion with my Year 12s yesterday night. They were saying, oh, they took out all the fun stuff from the new syllabus. So, yeah, you get to miss out all the fun and all the torture as well, I guess. But it is what it is. Let's move on. So, sine theta equals 0. We've done this one before. 0, 2 pi. Sorry, I'm getting a bit chatty today because I guess trigonometry is not exactly the most interesting of topics. All right, so 0 pi, 2 pi. Yeah, just observe it from the graph when it's 0. And this guy here, all 4 quadrants. Yeah, reference angle is pi on 6 or 30 degrees basically. So the answers should be pi on 6, second quadrant pi minus pi on 6, third quadrant pi plus pi on 6, fourth quadrant 2 pi minus pi on 6. Okay, and then you evaluate that. Pi on 6, 5 pi on 6, 7 pi on 6, 11 pi on 6. All right, so those are your answers. So let me just super highlight it for you. 0 pi, 2 pi, and then these guys. So all of them are answers. So that's 3 plus 4, 7 answers in total. All right, so to summarize, this is a two-part question. First part is show the identity. So you just show the identity using the clues within the question. The two major clues include the compound angle identity itself, as well as the final result. The second one is then you use that result, stick that into the equation, and then you try to simplify, collect the like terms, factorize, and then solve the two components, and you should be able to get the answers. All right, that is it. So I'm hoping that you have found this helpful. So I might move myself to the center. I'm hoping that you found this helpful. I know trigonometry is something a lot of year 11 struggle with, but I can't emphasize enough how important it is you master the foundations, because otherwise, believe me, when you go into year 12, it's going to be much more advanced work. So put in the work now, go through the pain now, master it, understand it, yeah, kill the upcoming prelim exams, yeah, show the teachers you've got it. All right, so if you have any questions, comments, leave a comment down below, or you can Facebook us, email us, check out our website. Yeah, you can contact us in so many ways. So questions, comments, if you want me to do a particular topic, just let me know. Bye for now.